It's often the case in mathematics that two varying quantities will change with one another. If we're talking about a constant rate of speed for an automobile, then time is related to distance. That is, as time changes, so does distance. If a person is working for an hourly wage, then the number of hours worked corresponds to the amount of a paycheck at the end of a week. Well, this creates an idea for a relationship between variables. And the notion of relationship leads to a very special kind of relationship mathematically called a function. We're going to define function here, and there are a lot of different ways to define function. This is the easiest one that I've ever seen. All the definitions, though, are consistent with one another. All right, first of all, let's define the notion of relation, and we can think of it as relationship. A relation is just a set of ordered pairs, and there may be a relationship between those ordered pairs, you see, between the items in the ordered pairs. All right, so if a relation is a set of ordered pairs, then a very simple relation would be the set consisting of these three ordered pairs. There's a relation. All right, back over here. Let's define domain of the relation, of our relation here, as the set of first elements, and range as the set of second elements. So the domain would be the set of first elements. Well, that's just 1, 2, and 3. The set consisting of 1, 2, and 3. The range is the set of second elements. Well, that would be the 2, 4, 6. You see, domain and range. Now, you may be asking, well, gee, why did I use the words first element and second element? Why didn't I just say the domain is the set of x values and the range is the set of y values? That's all there is to it. If we're talking about XY pairs here, well, yes, that's true in this particular situation. But we don't want to confine ourselves to an XY kind of relationship. There may be a distance-time relationship, you see, a D and a T relationship, and other letters may be involved in the idea of relation. So we don't want to limit ourselves in that way, and that's why I use first element, second element. But for conversation purposes, it's okay for understanding to think about x and y in terms of domain and range. Okay. Now, a function is just a special kind of relation, and here is a definition. A function is a relation in which every element in the domain, every value of x, if we're thinking of x's and y's, corresponds with exactly one element in the range. So a function is just a set of ordered pairs in which for every value that x takes on, there is exactly one value that y takes on. All right, sort of using primitive graphs, the situation looks like this. Now, in our domain and range values here in the previous example, we had 1 associated with 2, 2 associated with 4, 3 associated with 6. Now, do we meet the definition of function for this particular relation? Well, let's see. Is it true that for every element in the domain, there is exactly one element in the range? Well, does this guy have one partner over here? Yep. Does this guy have one partner over here? Yep. Does this have one partner over here? Yes. So this is a function type of relationship. How about this one? Now, notice the correspondence here. We have 7 corresponding with 4, 8 corresponding with 5, 9 corresponding with 5. Do we meet the requirements of function? It turns out that we do here because every element in the domain corresponds with only one element in the range. Now, these two guys happen to be corresponding with the same element in the range, but that's okay. You see, we have only one value in the range associated with 8, only one value in the range associated with 9. And by the way, there could be other items in the range. The range could include 1 and 10 that have no correspondence with items in the domain. It's okay. If we had other items in the domain, though, we would need to have partners in the range corresponding with them. That's this idea of exactly one. That means one and only one. So we have to have a partner and only one partner, you see, in the range for us to have a function relationship. All right, here's an example of a non-function relationship. We have 7 and 8 in our domain, and the range consists of these elements. And the correspondences are 8 corresponds with 6, 7 corresponds with 4, 7 also corresponds with 5. And this situation is what causes this to be not a function relationship, because 7 corresponds with 2 items in the range. Now, we're going to look at a lot of different ways to describe relationships. You know, we can describe relationships in mathematics between variables with ordered pairs. We can describe relationships sort of verbally. We can describe relationships graphically. We can describe relationships with an equation. And we're going to take some time here and talk about function versus non-function in all of those various situations. Here we're looking at ordered pairs. Now another way to kind of look at the situation, it's kind of paraphrasing what we have here, is this, that every value that x can assume is associated with only one y value. You see, it's the same exact idea. We just don't like to confine ourselves to x's and y's. And by the way, I'll tell you also that this definition in some textbooks for domain and range describes them as independent and dependent variables. And that's not too foreign to us either. If we're talking about building a table of values, and you know, we build our table of values, we put an x and a y, and we have columns, and then we choose at random values of x, a lot of times, and then we generate values of y according to the values of x that have been chosen. So we can think of x as, those x's that we've chosen, as being independent. They're just chosen out of the sky. And then the values of y that come out of that turn out to depend on the values of x that we've chosen. So we can say that the values of x are independent variables or independent values, and then the values of y are dependent. So that there's a nice correspondence with our experience there. All right, let's look at a few situations. Here's an equation, and we're going to go through the process of identifying domain and range here and deciding whether or not we have a function kind of relationship in our equation. Now, in our past experience, domain was kind of loosely described as acceptable replacements for x. And that's very consistent with our idea of domain here. Domain is all of the set of first elements, you see, if we're talking about ordered pairs. And for equations, it's for what values of x is this relationship or this expression defined? Well, gee, this makes sense for all values of x. For all real numbered replacements for x, 2x minus 3 makes sense. So the domain is all real numbers. And it turns out that the range is all real numbers as well. That is, y can take on values for all real numbers as x changes value in this process. All right, let's get to something a little more interesting. How about y equals the square root of x minus 3? Aha, now we have a domain that's not all real numbers, because the acceptable replacements for x are those values of x for which the radicand is positive or 0. So that means that x can only take on values greater than or equal to 3. So the domain would be x is greater than or equal to 3. Now, the range is pretty easy to identify as well. When x takes on those values 0 and greater than, x takes on values 3 and greater than 3, the radicand is 0 and all positive numbers. All right, now what do we get when we take the square root of 0 and all positive numbers? Well, y would be positive, that's all, or 0. So the range is y values greater than or equal to 0. Now, we're not here, though, to talk about domain and range. We're here to talk about whether or not we have situations involving a function. So let's make that decision. And we make the decision according to the definition. Does it meet the definition of function? Well, let's see. Is it the case that for every single x that we choose in this group of numbers for the domain, for every x that we choose, we get exactly one value of y? That is, if x is replaced with 10, we would have 2 times 10, 20. 20 minus 3, 17. So y is 17 when x is 10. Is there any circumstance where we would have an x replacement here and 2 values of y? No! And therefore, this does represent the function idea. That is, y is a function of x. What about here? Is it the case that every time we choose a different x, we get only one value of y? Well, yes, that's certainly true here. If x is 4, 4 minus 3 is 1. Square root of 1, the principal square root of 1 is 1. So that ordered pair is in our solution region here. It's part of the graph here. And it illustrates the idea that one value of x gives rise to or causes only one value for y. Now consider this equation. Now this equation does not represent a situation where y is a function of x. And it doesn't, because of this, it doesn't meet the definition. And here's why. All right, if we take this and solve it for y, then using the square root property, we find that y is plus or minus the square root of x minus 3. Now let's let x take on a value like, oh, let's say 4. So we would have, let's see, 4 minus 3 is 1, square root of 1, plus or minus the square root of 1 is plus or minus 1. So when x is 4, y is plus or minus 1. So it means then that two solution points associated with this equation, two coordinates that cause this to be true are 4, 1 and 4, negative 1. It means for a single value in the domain, there is more than one value in the range associated with it. So here, y is not a function of x. There is a rather special notation associated with functions. Consider this equation, y is 2x minus 3. It does turn out that y is a function of x here. And function notation associated with this could be f of x is 2x minus 3. Now I read this f of x, but it doesn't mean f times x. F is just the name of the function. Now that name could be George or any other kind of name, but George has too many letters, so we just use a single letter for the name of the function. And x is the variable that we see here. So f is the name, x is the variable. Now the name could be f, g, h. Those are kind of traditional letters used to name functions. Now if we interpret this f of x in a particular way, then this notation leads us to a technique for evaluating functions for a particular value of the variable. Now we can interpret this as the value of f at x. You see, and if we pop in a value, a particular value like 4, then this means in the f function, replace x with 4 and evaluate. We're finding the value of f at 4, you see. And we would then make the substitution, replace x with 4 and evaluate. And let's see, that's 8 minus 3 or 5. Suppose we make the request of f of x minus 3. Then this means in the f function, replace x with x minus 3 and evaluate. So let's replace x with x minus 3. Now we're replacing this x with x minus 3. So instead of 2 times x, it's 2 times x minus 3, and then minus 3, you see. So we have 2x minus 6 minus 3, or 2x minus 9. Here's another one. This function's name is h, and the variable is t. So h of t is equal to this expression. H of 3 means in the h function, replace t with 3 and evaluate. So let's see, this t is replaced with 3, and this other t is also replaced with 3. So we have 9 minus 6, or 3, as h of 3. Here we have h of t plus 2. It means in the h function, replace t with t plus 2. So we have, let's see, t plus 2 squared minus 2 times t plus 2. And away we go with evaluating, just simplifying here. Now, before I go on with that, though, I want you to realize that this letter could be r. If this were r plus 2, we would put r plus 2 here and r plus 2 here. Doesn't have to have the same letter correspondence as we had up here. It could be a different letter. It could be any number of things. And it's important to think of this replacement here as kind of a blind replacement. All you want to do in the first step is blindly replace the letter you have up here with whatever is in this parenthesis. That's kind of the way you want to think about it. All right, let's see. Squaring here, we get t squared plus 4t plus 4 minus 2t minus 4. And collecting here, t squared, 4t minus 2t, 2t, 4 minus 4, oh happy day, they go out. So this is h of t plus 2. Here's another one. What if I requested h of oh, let's say, happy face. Now here we have to think of this as a blind replacement. We're blindly replacing t with the happy face. So it would end up being, well, let's see, we have t squared minus 2t, so it's happy face squared minus 2 times happy face. There we go. Here's a rather special calculation dealing with the function notation. It says for f of x equals this expression, find f of x plus h minus f of x all over h. Now, this rather special form is called a difference quotient, and it's used often in calculus. Now, the evaluation goes like this. This says, in the f function, replace x with x plus h. So here we go. Just with this part now, replace x with x plus h. So we would have this x and this x are replaced with x plus h. You see, we're going to write this whole expression and replace x with x plus h. So we'll have x plus h squared minus 4 times x plus h plus 7. All right, this then is f of x plus h, because we've taken this expression and for these two positions of x we have replaced with this binomial. So binomial squared minus 4 times binomial plus 7. Binomial squared minus 4 times binomial plus 7. And it's really important, if you're evaluating these rascals, these difference quotients, to really take that much care in the substitution idea. That's where all the mistakes are made. Once the overall substitutions are made, then very few mistakes are made. All right, minus f of x. Well, f of x is this expression. So it's minus the f of x expression. Now notice I've introduced a parenthesis here because I'm writing a trinomial. And I want to make sure we're talking about subtracting the entire trinomial and not just the first term of it. All right, and then all of this is over h. Now notice, no function notation in this denominator. All we're doing is writing h. All right, all the action is in the numerator here. Let's see, x plus h squared, that's x squared plus 2xh plus h squared. Then minus 4 times x plus h is minus 4x minus 4h plus 7. And then minus all of this means change all those signs. We have minus x squared plus 4x minus 7. All of this is over h. Now, typically, some very nice things happen algebraically here in evaluating difference quotients. For example, I have an x squared here, and I have an x squared here. So I have x squared minus x squared. Those go out. And then I have, let's see, 2xh and no other xh's. So I have 2xh left in the numerator. I have h squared here and no other h's. So I have plus h squared. I have minus 4x plus 4x. Those go out. I have minus 4h and no other h's. And I have 7 and minus 7. Those go out. So a lot of things kind of drop out by themselves, and then all of this is over h. Now h divides every one of these terms in the numerator. That's one way to look at it from here, or I can just factor in the numerator, pulling out an h, a common factor of h. Now if I pull out the common factor of h, let's go out to the side. H is here, here, and here. So I have h times 2x, h times 2x plus h minus 4 all over h. These go out, and I have this numerator as the result of all of this. So it's kind of algebra intensive a little bit, but the key is the replacement here in the very first step, this f of x plus h. In the f function, replace x with x plus h. So just imagine this binomial going into both of these slots and writing down the whole expression like that. That's the key. To evaluate whether or not a relationship between two variables is a function relationship, we can make that evaluation both algebraically and graphically. And it turns out that the graphical evaluation is much easier than the algebraic one. For the algebraic one, we have to kind of meet the definition for function. We have to ask ourselves if it is the case that for every value taken on by the independent variable, x in most cases, do we have only one value of y? Do we have only one y partner? And if that's the case, then we have a function, and if it's not, we don't have a function. Well, here we would evaluate algebraically. We could say for every different x, do we get exactly one y? Yes, that's true. But graphically, we can even see it more clearly. It is for each x value in the domain of this function, do we have only one y partner? For this x, one y partner. For that x, one y partner. For this x, one y partner. For that x, one y partner. For this x, one y partner. For every x in the domain, we have exactly one y. It meets the definition of function. So here we have the graph of a function. Now, what about for this? Now, algebraically and graphically. All right, algebraically, we can evaluate kind of like this. We might come out to the side and solve the rascal for y, and we can see it very clearly. Now, I think we looked at something like this before, but if I add 2 on both sides, I have x plus 2 equals y squared. And then y then is plus or minus the square root of x plus 2. So the idea is that x can take on a single value, and y will take on 2 values. So when x is, let's say 7, for an x of 7, we would have 7 plus 2, 9, the square root of 9, 3, plus or minus 3. So y is plus or minus 3. And that means one value of x is giving rise to 2 values of y, not a function relationship here. All right, now graphically, we can see it more clearly, or as clearly, I guess, but much faster. And it's evaluated like this. For this value of x, we have 2 values of y that place points on the graph. You see, so for one value of x, we have 2 values of y that put points on the graph, and that's all there is to it. Now, this idea of a single value of x putting 2 values of y, or associated with 2 values of y for points on the graph, gives us a way to make this test for functionality like this. It's called the vertical line test, because it turns out that if we can imagine a vertical line intersecting the graph, and if that vertical line intersects the graph in more than one point, then we have that condition where one x is associated with 2 y's. You see, and so we don't have a function. Now, if a vertical line anywhere in the domain of the function intersects in only one place, like here, you see, I'm performing the vertical line test. Now, you do this mentally. You don't actually draw the lines, but it's the idea that you imagine vertical lines, and if they intersect the graph at only one point, then you have a function. If the vertical line intersects in more than one point, then you don't have a function. Let's evaluate some others. We have a kind of a curvy looking graph here. I'm looking at it like this, evaluating it with a vertical line test, and every vertical line intersects the graph in only one spot. So this is the graph of a function. Now, what about for this one? Well, it passes a vertical line test over here in this part of the domain, but it fails a vertical line test here. And therefore, this is not the graph of a function. Here also is a situation where we pass the vertical line test in one part of the domain of the function, but we fail the vertical line test here. And so this is not the graph of a function. Now, here we have a curvy graph, but it passes the vertical line test, and therefore this is the graph of a function. When applying the fundamental operations of adding, subtracting, multiplying, and dividing to functions, the situation is handled in exactly the same way we would expect. For example, if we have these two functions and we want to add them, we would describe the addition as f of x plus g of x. Well, just replace f of x with the expression, g of x with its expression, and then add the two expressions. Here we're dropping parentheses and collecting like terms. A notation that's used to describe the addition of functions is this. It's f plus g of x. It's the addition of the two functions, and x is the variable involved. So f plus g of x would be the 5x plus 4 that we found here. Now we can use this kind of notation to indicate subtraction like this. So this means the difference of the two functions, but I suggest that we write this the way we would understand it. This is f of x minus g of x, you see. And now the substitution is particularly easy. The f of x function, the g of x function, the subtraction of the two, it's a real clean kind of process. Drop the parentheses, we're changing signs over here, collect like terms, and we get this. So f minus g of x is 3x minus 6. Now, suppose we take the same two functions we had before, and we want to find f minus g of 7 of a particular value. There are actually two ways that we can proceed here. We can say, well, gee, we understand that this notation means the subtraction of functions, but now the x has been replaced with 7. So really, what we're talking about here is f of 7 minus g of 7. And we can follow our nose through that kind of notation. F of 7 means in the f function, replace x with 7 and evaluate. So in that f function, we replace the x with 7. So that's 4 times 7 minus 1. You see, and then minus g of 7 in the g function, replace x with 7 and evaluate. So this x would be replaced with 7, so we would have 7 plus 5. And now, let's see, we'd get 4 times 7, 28, minus 1, 27, and then here we have 12, 27 minus 12, 15. Another way to deal with it, though, is like this, that using this notation, we can think, well, we've already figured out f minus g of x. We know that f minus g of x is 3x minus 6. We just figured it out in the previous problem. You see, you find the f minus g of the variable first, and then f minus g of 7 means in this f minus g function, replace x with 7. So here's the f minus g function, and we replace x with 7, and we get 15 as expected. So really, when we are adding and subtracting functions, and then in a moment multiplying and dividing, we're really defining a new function. We have a new function, and we could say that its name is whatever operation we're performing here. Multiplication, same idea. F times g of x means f of x times g of x. And for the functions we've been talking about, it would be 4x minus 1 times x plus 5, performing the indicated operation. Here we go. F over g of x means the division of the function, so it's just f of x over g of x. And the f function was this, the g function was this. Now do notice here that because we have the introduction of a variable into a denominator, we have a limitation on the domain. And the original functions didn't contain that kind of limitation, that the domain here for this expression, the acceptable replacements for x, would be all real numbers. And for this one, separately, would be all real numbers. But when we make a quotient out of them, we have a situation where we can't let x take on the value -5, and so we have a limitation on the domain. So it's kind of a nuance in this situation of fundamental operations on functions, where we have to kind of look at the situation involving domain as we get to an answer. Here we have f of x and g of x, different functions now for a change. F over g of x would be this quotient then. And now think about the domain. Well, we have a limitation on the domain in the numerator because we're talking about the square root of a radicand that must be positive or 0. And the values of x that will cause the radicand to be positive or 0 are values that are x that are 3 or greater than 3. So x is greater than or equal to 3 for the domain of that numerator. And the denominator has a limitation as well. The limitation is that x can't take on the value 5. So the domain then of this quotient function, this quotient idea, would be this. Now, if we swap it around, if we just flip this over, it's a little bit different. We have to consider it somewhat differently, although it's very similar, but we just have to consider all the parts here sort of separately. G over f of x, the g function over the f function. You see, and now think about the limitations. Well, we can't have the value of the denominator becoming 0, and we can't have the radicand becoming negative. So let's see. For the radicand not to be negative, x would have to be greater than or equal to 3. But x can't be equal to 3 because it would cause the denominator to be 0. So we have a strict inequality then for the domain x is greater than 3. Suppose f of x is 4x minus 1, g of x is x plus 5. Now, it turns out that we can actually perform an operation, a new operation, where we put one function into another. Now, this is called the composition of functions. And it works like this. The notation is f of g of x. If we're putting the g function into the f function, this is the notation. Now, let's just kind of go through with the bracket notation here. Working inside the bracket, we would replace g of x with the expression for g of x. So this would be f of x plus 5. Now, this says in the f function, replace the x with x plus 5. So we're replacing x with x plus 5 in the f function. So instead of 4x minus 1, it's 4 times binomial minus 1. So 4 times x plus 5 minus 1. And then we would clean this up a little bit. 4x plus 20 minus 1, 4x plus 19. All right, so that's the idea. Now let's go the other way. Let's compose the two functions in the other direction. That is, let's put the f function into the g function. So it's g of f of x. And following the notation, it's g of, well, what is f of x? F of x is the 4x minus 1. And then g of that means in the g function, replace x with that binomial. Here's the g function, replace that x with this binomial, and we would have 4x minus 1 binomial plus 5. So 4x plus 4. We can even put a function sort of into itself. That is, f of x means we're going to put the f function into itself. So it is f of, now f of x is 4x minus 1. F of that binomial means in the f function, replace x with binomial. So the f function is 4x minus 1, so it's 4 times 4x minus 1 minus 1. We clean it up, we get 16x minus 5. Now, there is another notation for the composition of functions, and I'd like to show that notation to you. This is the easiest one to follow, but another notation for this is this. And I'll use it in all three places. This would be f of g of x would be f of g of x, like this. Now, this is not a 0, and it's not an O, a letter O. It's just a little bitty circle kind of thing. And the students read this as fog x. But f of g of x is what this says. That's the notation for it. And this is the equivalent notation. And I suggest that if you see this, you write that, because it's easier to progress through this than it is that, because we're unfamiliar with this somewhat. Now, this one would be gof x, or g of f of x. And when we're putting f into itself, it is f of x, like this. But we would write this and proceed from there. Many functions have associated with them another function called the inverse of the function. I'm going to show you how to generate the inverse of a function, and then we're going to investigate relationships between functions and their inverses. Suppose we start with this function. Now, to think about generating an inverse, we are taking the function in its manipulative form, the y equals 2x minus 3. And we're going to actually swap the role of x and y in this function. That's what inverse is all about. So to generate an inverse, we simply replace x with y and y with x. So y becomes x becomes y, and here we have the inverse of that function. Now, we wouldn't leave it like this. We would probably want to write it in some kind of function notation. So to do that, we need to first isolate y. So let's see. I'll add 3 on both sides. Then I'll divide on both sides by 2. I'm going to divide here by 2, divide here by 2. When I divide over here by 2, I have x plus 3 over 2. And when I divide on the right by 2, I have simply y. Now, normally we see the y listed on the left side of the equation, so I'll write it like that. Now, notice, first of all, that we have operations involved in this inverse function of adding and dividing. We're adding 3 here, we're dividing by 2. Look up at the original function. We're subtracting 3, we're multiplying by 2. Operations which are inverse to the ones that we saw down here. Kind of an interesting situation involving inverse functions. Now, just because we have inverse operations, though, doesn't mean that that's the way that we generate inverse functions. We generate inverse functions by saying inverse and then replace x with y and y with x and then solve for y. Now, there's a notation that indicates an inverse function, and it is this. If we want to indicate f inverse of x, the inverse function of f of x, you see, we would do it like this. F inverse of x is x plus 3 over 2. You see, this little flying -1 doesn't mean an exponent of -1 and therefore a misplaced base and all of that kind of thing. This isn't an exponent at all. It is the notation for inverse function. So this is read f inverse of x. All right, now let's look at this manipulation. Suppose we take our 2 functions, and I'm calling this g function. I'm calling this other function a g function. We know it to be the inverse of this f function. All right, so this is really f inverse of x. But a lot of times when functions come at us, we don't know whether we have inverses or not. And just for this process, I'm just giving it a different name. Okay, let's see what happens when we perform this calculation of the composition of functions in both ways. That is, we put g into f and f into g. Let's see. F of g of x means, let's see, f of, what is g of x? G of x is that fraction business. So it's f of the fraction. Now, f of the fraction means in the f function replace x with the fraction. So we're going to take that expression and replace x with a fraction. So we have 2 times fraction, then minus 3. 2's go out here, and we have x plus 3 minus 3. The 3's go out, and we have x. Interesting situation. Here we have, let's see, we're putting f into g. This is g of whatever f of x is. Well, f of x is this expression 2x minus 3. All right, now this says in the g function, replace x with 2x minus 3. So we're going to take this expression for the g function, replace that x with this binomial. So it'll be binomial plus 3 over 2. Binomial plus 3 over 2. Now when I drop parenthesis in the numerator, minus 3 plus 3 go out, and we have 2x over 2. Now the 2's go out, and we have x. So notice that in both directions we get x as the result of all of this. And it's simply because the inverse operations have tended to negate everything involved in our 2 functions. And so when we perform that composition, we're left with simply x. Now this becomes the acid test for whether or not we have inverse functions. Now we knew that we had them to begin with here, and I just wanted to show you the manipulation. But if you're asked to show that 2 functions are inverses of one another, then what you do is perform the composition of the 2 functions in both directions and verify that you get x in that calculation. Let's take a look at another situation. Suppose we start with this function, and we identify first its domain and range. All right, think about domain. We've got the acceptable replacements for x. Well, let's see, all x's are okay except for that particular x that will cause this denominator to become 0. The denominator becomes 0 when x is 5, so the domain would be all real numbers except 5. X is not equal to 5. Now, the range is a little more elusive, and we haven't concentrated a great deal on identifying range, but let me just tell you this, that the range would be all real numbers. And in identifying range, we're saying, what values can y take on? That is, in this form of the function, for all of these numbers except 5 that we replace x with, what kinds of numbers come out for these fractions? You see, what values can y take on? Well, it turns out that y can take on any value in the world except 0. This fraction can never become 0. And the reason is because fractions become 0 when their numerators become 0. And this fraction doesn't have a letter which can take on a value which will cause the fraction to become 0. And so our range then would be all real numbers except 0, or we list the range as y is not equal to 0. Now let's look at the inverse. All right, to calculate an inverse, we replace x with y and y with x. The y becomes x, and the x becomes y. And now we solve for y. Now to solve for y, I would first clear the fraction by cross multiplication. Think of this as x over 1. When I go in this direction, I have x times y minus 5. So let me go ahead and with the multiplication. It's pretty simple here. X times y is xy, then x times minus 5 is minus 5x. And then on the right, 1 times 2, 2. And now I would add 5x on both sides to find xy to be equal to 5x plus 2. And now I would divide on both sides by x. So I'm dividing through by x. And when I divide here by x, I'm left with y. When I divide this term by x, I'm left with 5. When I divide here by x, I have 2 over x. Okay, so now this is our inverse function. Let me write it up here. I'd like to write it in y form. I could use that little inverse function notation that I had earlier, but I want to write it just like this because I want to identify domain and range. So you might think about this as I transfer the problem up here. Okay, so for this rascal, domain. All right, let's see, the domain, the acceptable replacements for x. Well, we can replace x with any value in the world except for that value which will cause the denominator to become 0, and that value would be 0 itself. So the domain would be all real numbers except 0, or we could simply say that x is not equal to 0. What about range? What about range? Well, let's see. What values can y take on? We have 5 plus some fraction over here. But the fraction, we know, can never become 0. It can't become 0 because there's no variable up here that will cause, there's no variable which can take on a value which will cause the numerator to become 0 and therefore the fraction to become 0. So this fraction will always have value. Might be positive, might be negative, but it'll have some value. So we're taking 5 and we're adding some value to it, you see. So this y can never become exactly 5. So the range would be all real numbers except 5. Y then is not equal to 5. Now the purpose of this little demonstration is to show you the relationship between domain and range in a function and its inverse. I want you to notice that the domain of the function corresponds with the range of its inverse, and the range of the original function is the domain of the inverse. Now, and this situation works both ways, in both directions. That is, these functions are inverses of one another. We could have started with this function. We could have said, okay, here's our original function. Now let's generate its inverse. We would be generating that, you see, and we could go through this domain and range situation in the other direction. So domain and range. All right, here's another situation. This is one of the most interesting, I think. It's the graphical relationship between functions and their inverses. All right, let's consider first of all f of x to be this and then g of x. Here is its inverse, as we have seen before. Now let's suppose I'm graphing. Now think of this as y equals 2x minus 3. I think of that as y equals the fraction. Now I generate a table of values. Okay, I pop in a few points for x and I solve for y. Now, I want you to notice what happens if I begin to generate this table of values. Suppose I let x take on the value, let's say -7. Now, I'm going to choose values for x that are convenient for this calculation. Suppose I choose an x of -7. I would have -7 plus 3, that's -4. -4 over 2 is -2. Now let's suppose I choose an x of, let's say -3. That's pretty trivial. -3 plus 3 is 0 in the numerator. 0 over 2 is 0. Now an x of, let's say 1. 1 plus 3, 4. 4 over 2, 2. What about an x of, let's say 5? 5 plus 3, 8. 8 over 2, 4. Now look at these two tables of values. Notice that the items in the x column here correspond precisely with the items in the y column over here. And the items in the y column here correspond with the items in the x column here. Now this is no more than an extension of that idea that the domain and ranges of these two have just swapped roles, pretty much. So in generating a graph of an inverse function, we really don't need to make that table of values. Or I should say it this way. We really don't need to evaluate the function to make the table of values. All we need to do is take this rascal right here and just flip it around like this. You see, put this x column in the y column over here, and put this y column in the x column over here, and away we go, plotting points and so forth. Here's what the graphs look like. Here's the graph of f of x, and here's the graph of g of x. Now, there doesn't seem to be any discernible relationship between the two graphs, but there is really a rather intriguing one. I'm going to draw a line here just for demonstration purposes. This is the line y equals x, and it's a line that goes through the coordinate plane like this. Just kind of a 45-degree line like this. It turns out that the function and its inverse are reflections of one another in this line. That is, by reflections I mean, if we took this point and sort of attached the f function, let's just attach it right here, and then swivel it around, you see, at that point, then we would get the g function. So a reflection in the y equals x line. Interesting situation. Now, why did it do that? Why did it do that? We're swapping the roles of x's and y's. We understand that much. But why do we have this reflection in the y equals x line? Well, it's because of this. We know that on the x-axis, positive values lie out here, and negative values lie to the left. And on the y-axis, the positive values are above and the negative values are below. Now, when we swap the roles for x's and y's, we want positive x's to swap with positive y's. You see, I mean, we want a role reversal that is true to the signs. You see, positive x's with positive y's, positive x's. Negatives with negatives in the same way. Okay, now how is that accomplished? If we had taken a graph and simply, well, think of the coordinate plane now. If I just take the coordinate plane and twist it this way, boom, then yes, I would have a situation where these positive y's would become positive x's. But the whole thing is revolving this way, or sort of twisting this way. And look at what happens to these positive y's. Boom, they become negative x's. That's not what we want. You see, so we have to find a way to swap positives for positives, and that is by doing this. Boom. When you do a swap like this, these guys swap around for those, and those guys swap around for these. You see, positive to positive, and negatives to negative. Same idea. So that's why we have that reflection in the y equals x line. Let's generate the inverse of another function. Let's start with f of x is x squared minus 2. We would write this as y equals x squared minus 2, and we find the inverse by swapping the role of x and y. Y becomes x becomes y, and now we want to solve for y. We'll add 2 on both sides, swap sides, and now if y squared is x plus 2, y then is plus or minus the square root of x plus 2. You see, by that square root property, but we kind of see algebraically here that we don't have a relationship between x and y, which is a function relationship. That is, y is not a function of x, because a single value of x can generate 2 values of y. Namely, if x is 7, we have 7 plus 2, 9. So y is plus or minus the square root of 9, plus or minus 3. So when x is 7, y is plus 3 or minus 3. Therefore, we now have this function idea. Now let's look at it graphically. We may recall that this is a parabolic curve with minus 2 on it. Means the parabola is just 2 down on the coordinate plane. So this is the graph of f of x. Now its inverse is this graph. This is the graph of its inverse. It's an inverse relationship, but that relationship is not a function relationship. Now we know it's not a function graphically because it fails a vertical line test. But you know what? We can sort of analyze this situation backwards. We can look at graphs and be able to tell whether or not inverses of those graphs are going to be functions. Here's what I'm talking about. Now, let's kind of work backwards. We know that the inverse is not a function because it fails a vertical line test. But we also know the relationship between graphs of functions and graphs of inverses is that they are reflections in the y equals x line. Let's see. Here's the y equals x line. You see, we have this twisting around that y equals x line. Let's twist back. From here, we twist back to that. So what I'm showing is that this vertical line test on the inverse is the same as, or corresponds with, a horizontal line test on the function itself. So if the original function fails a horizontal line test, its inverse will fail a vertical line test. On the other hand, if the original function passes a horizontal line test, then the inverse will pass a vertical line test. Let's practice the situation. Over here, we have, let's see, we have a function here. We know it's a function because it passes a vertical line test. Okay, now, what about a horizontal line test? Well, we have failure of a horizontal line test, so we know that this rascal's inverse will not be a function. All right, now what about this one? Well, let's see. We are passing a horizontal line test. Do we pass it all the way down? Let's see. Sure, we pass a horizontal line test on the function, so its inverse will be a function. Here's a situation where, let's see, we are passing a horizontal line test. We pass the horizontal line test, therefore the inverse will pass a vertical line test. On this one, horizontal line test, we pass the horizontal line test, but I tricked you. This isn't a function to begin with. It fails a vertical line test to begin with, so that one's out of the discussion anyhow. Okay, so we have situations where we can identify whether or not the inverse is going to be a function by looking at the graph of the function itself. If the graph passes a horizontal line test, then the inverse will pass a vertical line test and therefore be a function. All right. Now, that situation mathematically is called one-to-one, and the graph is continually increasing or decreasing. Look at these two graphs. This one continues to decrease throughout the domain. Throughout the domain of the function, it's just decreasing all the way. This one is continually increasing throughout its domain. So no wonder you see, if it went to a certain point and it was increasing and then it began to decrease anywhere, then it would fail that horizontal line test. So it has to continually increase or continually decrease. Now this one-to-one idea is this, that it means that for every one value of x, there is one value of y. And for every one value of y, there is one value of x. That's just the nature of functions that have graphs that are continually decreasing or increasing. For every one value of x, there is one value of y. 1x, 1y, 1x, 1y, 1x, 1y, 1x, 1y. And also 1y, 1x, 1y, 1x, 1y, 1x, and so on. Okay. Now, come back to the original problem. Let's talk about domain a little bit here. We have a domain of this function which is all real numbers. Now I wonder if there's some way that we can sort of redefine the domain of this function so that we'll have an inverse which is a function. Well, let's look at the graph for some assistance. Here's the graph of the function. It fails a horizontal line test. We know that it would pass a horizontal line test if it were continually increasing or decreasing. So, if we took out this part of the graph, if we only defined the function, you see, for the values that lie out here, then it would have a graph that's continually decreasing. On the other hand, whoops, almost dropped my chalk. I juggle part-time, you know. If I take out the negative x's and just define the function from here out to the positives, then I'll have a continually increasing graph, and therefore the inverse will be a function. Well, let's do that. Let's limit the domain in some way. Let's limit the domain to positive values or 0. That is, I'm going to define this as x is greater than or equal to 0. Now, I can also go through a little discussion about range. Let me make this a little more clear by saying D for domain. The domain, x values greater than or equal to 0. Now for range, let's look at the graph and tell, for the range, let's see, what values of y happen to appear on the graph. Well, it's y values from here all the way up. So it's y values from -2 to infinity. So greater than or equal to -2. So I'm going to write y is greater than or equal to -2. Now, graphically, here's what I've got. I've limited the domain, so this part of the graph is no longer valid. It's out of here. All right, now, think about the inverse. Now, we're going to come back to the algebraic form in just a second and see what happens algebraically. But graphically, we know that if I have this as the graph of the function, then its inverse will be a reflection in the y equals x line. And if we attach it right here, if we attach the graph right here and kind of twist it around, it'll just be from here up here. So all of these values are going to be gone. Now let's see if we can't verify that idea algebraically. We know conceptually that this is what needs to happen, or this is what sort of happens with functions and their inverses graphically. But what about algebraically? Okay, we have a domain and range that we've identified for the function. We go through this inverse process. Now, we just talked about the notion that the domain of the function becomes the range of the inverse, and the range of the function becomes the domain of the inverse. The range of the function is y values greater than or equal to -2. So that means that the domain down here will need to be x values that are greater than or equal to -2. And the range down here will be y values that are, well, let's see, the domain x is greater than or equal to 0, so y would be greater than or equal to 0 down here for the inverse. All right, how does that affect this situation? Well, let's see. The domain is greater than or equal to -2. Gee, we kind of know that from the nature of the radical here. If we have the square root of x plus 2, then the only values of x that make any sense are values of x that are greater than or equal to -2. So that was kind of predetermined. The range, though, is a little bit different. Now, this says that the range needs to be y values greater than or equal to 0, but for these to be greater than or equal to 0, we would have to take out this plus or minus. We would have to take out the minus part. We would only want the principal square root. So I can just erase this, and now I have y values that are positive or 0. You see? So now I can call this the inverse function. That is, I can say that this expression is f inverse of x. And I can write it like this. Well, the calculator has some rather special capabilities when it comes to graphing functions and inverses. Let's have a look. I've already entered y equals x squared minus 2, and the expected graph looks like this. If we wanted to enter the information about drawing its inverse, we could do it like this. We could go down and actually enter those two equations that would give the inverse relationship. Now, one of them was the square root of x plus 2. I'm opening a parenthesis here, x plus 2, and close parenthesis. And let's look at these two graphs first. All right, now the other one will complete the graph of the inverse relationship, and it is the negative of the square root of x plus 2. And here's the other graph that will form that complete inverse relationship, but not an inverse function. Now, this graphing calculator, though, has a very special capability. I'm clearing this equation, and I'm going to clear this one. And I'd like to show you, here's the graph again of the original equation, or original function. The graphing calculator is capable of just constructing the graph of an inverse, whether the inverse is a function or not, all at one time. If we press clear at this point, we'll get an empty screen. And from here, we access the draw menu. Now, to do that, press second and then the button marked program. The second function on program is draw, so it's actually second, and then we're accessing draw. Here's the draw menu. Let's cursor down. There are a number of options here, and it's option number 8 that we want. Here's draw inverse. When we press enter, here's what shows up. Draw inverse of what it's saying. Well, we want to enter Y1. Now, to access Y1, it's the Y variables menu that we want. So press VARS and cursor right one time. It's a function, so I'll press enter here and then enter again because it's Y1. Now, draw inverse of Y1 is what this is saying, and it's going to draw it right on top of our original graph once I press enter. And here is that inverse relationship, which is not a function.